All right. So we're going to go ahead and do the next talk by Leo Martinez. Wow. Sorry.
No, it's okay.
By you.
Leo Martinez.
Thank you. Automatic crater detection and characterization.
So if everyone can me, let's go. Wait for the
Actually, turn this microphone off. There we go. Now it's back on.
Do everyone hear me? Yeah, sounds
Yes.
good. All right. So, thank you all for giving me the opportunity to present my work in this wonderful workshop. For those who were not here this morning, sorry. I'm Leo Martinez. I come from Paris-Saclay University. And in this presentation slot, I will present you the work I conducted during my PhD, which comes to its end since I will defend my thesis in precisely 2 months from now. So yeah, let's go. Oh, it doesn't work. I can't. Oh yeah, okay. Sorry. So as you all know, here craters are probably the most common geological feature that we can find on every planet through the solar system, from the moon to small bodies, to Mars, and even on Earth. And it has been historically used for dating purposes. Indeed, it has been historically shown during the 17th that by making the correlation of the crater density with respect to the crater diameter, we can be able to find the age of the specific geological region that we study. And this is very interesting, but all the purposes of this job is to correctly count the crater and correctly detect them. Indeed, here you have an example of a Noachian region on Mars, and you can see that when it comes to count the small craters, the task become a little bit harder. It has been shown that after 30 minutes of this repetitive task, error started to appear. And that's why we wanted to automatize this task. So today, in my first part presentation, I will talk about crater detection, and then we will see if we can characterize them geomorphologically. So crater counting is not something completely new in literature. I put here some very recent articles, some examples of studies that tried to solve this problem. And I will show during my presentation that when we interest ourselves at the small how to say that, when we want to do it properly, there is a lot of problems. So let's continue. So in order to count craters with artificial intelligence, we need data to learn. And for that purpose, we took the Mars Global Crater Database made by Anthony Laguin and collaborator, which manually verified the wonderful database that you made 10 years ago from now, more than 10 years ago. Sorry. And
from a high note to a low.
And the authors of this study not only verified the crater, the original crater database, but also labeled them with a few geological features that interest us. I will. Is it a laser that I can use, or?
Yep.
here on the left for the people on Zoom, we have a very specific morphological pattern that occurs when there is water in the subsurface, which I'm sure a lot of person know, which is layered craters. Here we have ghost craters, which are craters that were erased by erosion or by a resurfacing event. Here in green, we have secondary craters, which are the products of primary impacts, and the other class is the regular craters, which have nothing particular to declare. And so, in order to detect craters in images, you need images, of course. So for that, we took the last version of the CTX mosaic, which covered 99% of the planet at 5 meter per pixel resolution. But we don't need that resolution actually, because we want to detect in this study craters bigger than 1 kilometer. So in order to not be polluted by very, very small craters in the images, we downgraded the resolution to 100 meters per pixel. And then we merged the tills, because of course you can't download the whole 5 tera database in one hour. So we merged the tills in a very specific pattern. I can come back later on this if you have question about that. And we split it into 3 different databases. One for the training of the model, one for the validation step to verify that the training is happening correctly, and the test version is an independent database where we want to do science, and we yeah. And then, last but not least, we cut our big images patch into 512 per 512 image patches, in order to have with resolution, in order to learn the scale, the famous power law scale of the craters during the detection steps. Okay, so as a model, we used a non-made faster RCNN model that we developed ourselves, and we trained it for 30 epochs. The model was provided by actually it's not a really new model. It's kind of a pretty old one, but easy to understand and to make works. And yeah, it works pretty good. So in the next part of this presentation, I will just make like a parenthesis to explain you how we evaluate the model, and with what metrics. So the first thing when you want to evaluate a model is to know what is a good detection or no. So everything in this is a matter of threshold. You put a threshold, in general in literature is 0.5 on the IOU, so it's the intersection area between prediction and ground truth with respect to the union area. And you can see that if the prediction area match pretty good the ground truth, your IOU is higher than 0.5, and then you like this, you construct what is a true positive detection, a false positive, and a false negative detection, and then you count in a given image the number of true positive, false positive, and false negative in the image. And then with this, you construct 2 metrics that are very important by counting the number of true positive and true false, and false positive and false negative. The precision which we say basically if the algorithm is correct or not in the detection, and the recall or the sensitivity, which say that among all the craters that were present in the database, how many were correctly detected. And those 2 metrics are really important to evaluate deep learning methods. because they doesn't like we need each other to be sure that the algorithm work properly. But it's not really easy to manipulate to have two metrics. So we built another one that is we can find on deep learning papers, deep learning community, is the precision versus recall curve. Basically, you just sort all your precision with respect to the confidence score, which is a probability associated to the prediction. And you just say, okay, I want calculate the average recall for 40% of the best detection, for 45, 60, etc. And then you construct those curves. So there is multiple curves because as I said before, it depends on the intersect area and area of a union that you take, and it says basically how much you are strict on what you consider to be a good or a bad detection. And for binary problems like this, crater or not craters, we can use the mean average precision by doing the intersection, the area under the curve of this curve. And this is one of the most representative metrics in the literature of deep learning. So here we have a mean average precision at an IOU of 0.5 of 82%, which is very good. We did the same test with latitude ranges, and we can see that from the South Pole, South latitudes, performance started to drop a little bit, and we tried to understand why, and it's likely due to the presence of ice cap in the south areas that create sometimes circular shape geomorphologies, and that can be interpreted as craters, but it's not, so it's counted as a false positive, and it's not what we want. I would say that in literature, Benedicts and collaborator had the same problem, but at a bigger scale. Probably for them, it was due to the fact that they did not reproject their images. So the craters appears as not round in shape for the high latitude, and this caused them a problem. So we corrected this problem, and we still have a drop in performance for the south, but it's not that bad, and we can live with it. Here it's a result of an inference made on an independent image in the test area, so you can see that it's pretty satisfying by the view. There is still some errors here in the edge, but we can say that it's normal because it's a lack of context. And yeah. We tried to make an application, and another very good study which map the landing sites of opportunity rovers here, and so the author INEC in 2017 made this datation curve, and so we tried to make run our algorithm on it. And here is like a non-exhaustive list of inference images. And as you can see, in the range of crater that is common, we can see that we have a very good fit of the study of Heineck. So to conclude this part, I would say that we built a automatic detection model algorithm which work very satisfyingly. We have a good results, and we can do like science with it. It was validated on a statistically representative and independent data set, and this was published in a peer-reviewed journal. You can scan the little QR code if you want to have more informations. But we can go even further by doing classification of craters. And this is what I will present in the next slides. How many time do we have this?
You have about 14 minutes. There's actually an error on the schedule. My talk apparently takes no time. Goes from 3:30 to 3:30. I can guarantee you that it takes more than that.
Okay.
Oh, we're running 10 minutes behind.
Okay, okay.
15 minutes. 13 now.
Okay. Let's go. So let's go for crater classification. I hope you're ready. So here is a little geological context of the problem we want to solve. Here we have three types of geomorphology of craters. We have the regular one in blue, and we have in yellow what can be assimilated as a ghost craters. It means that it's a crater that was there before a resurfacing event, and so it is still visible, but it doesn't count if you want to date the surface. And also you have this little spot of ejectas here, which are secondary crater and which we don't want to count in the dating process. So you can choose to remove them by the end, but it's probably taking a lot of time. And so we will try to do it automatically. In literature again, there is several studies that tried to do this, but it's still under development. There is obviously the Lagan collaborator in 2021. We do that manually, but it's not the purpose of of this method. And we publish actually we submitted actually it's under review a way of doing it by using a deep learning algorithm. So again, the image we took the last version of the mosaic, but this time as a higher resolution, 15 meters per pixel, and we train a little model to classify the craters with respect to the geomorphological categories that I explained before. And here is the matrix of results. So this data set is a test data set, so it's an independent data set. And what we can see here, it's you can read it like this. You read the abscissa, like if you want to detect regular in 70%, 75% of cases, it detects correctly a regular crater, but in 10% of cases, it mismatch with a secondary crater. So we will explain later why, and we will discuss these results. But for other classes, secondary are well detected in 83% cases, layered in 84% cases, and ghost in 80% cases. So we did this accuracy. So accuracy means in a given sample of detection, you count how many were correctly detected, and you made like percentages, and we built this map of classification accuracy over our test data set. And in order to illustrate the performances of our model, I will show you two extreme bad and good results. So here is the bad result with an accuracy of 60%. And I will show you in details. Indeed, we can see in this set of 16 craters, it means 4 craters. It means it means 4 craters. And so the first column, we can't see correctly, but the first column, the first line, he was supposed to detect ghost craters. And as we can see, he misclassified these 3 ghost craters as a valid or regular one. But here is the thing is that the database has been labeled manually by operators that are like humans and that are subject to bias. And now I would ask you the question: if you will relabel them, maybe you will probably not have the same result as the originate operator. So this kind of study is still subject to the bias of human operator that first labeled the images. Otherwise, it's kind of what we expected for the prediction. This one maybe it's another bias because the majority of the secondary craters are small-sized craters, and this one, which is a regular one, was classified as a secondary, but we can see that it's a small one. So yeah, maybe that's another source of error. And I will here show you a pretty good, one of the best result that we have. And we can see that it's like what we expected to have. So we can see that statistically it worked like as a human being would have done the job. Here is the results, and as a little application for this algorithm, we made a datation on a given place on Mars, and we removed the secondary craters and the ghost craters of the counting of the detection, and we found an age. We calculated an age with crater stat, and we found an age which is in agreement with what we can find on literature. So we are really happy with that. In conclusion, I would say that we also successfully built an algorithm which is able to characterize the crater with respect to their geomorphological categories and with an accuracy which is like good for science, I would say. And we can see that there is still difficulties or drop in performances when we are on ambiguous cases. But actually, it worked like in a satisfying way. This work was also submitted to a peer-reviewed journal, which is under review. So for the final conclusion of this presentation, I will say that our work focus on the construction of a new pipeline which mixed detection and classification, which will be a new tool for planetary datation. And as a future work, we want maybe to extend this research to other planets, for example, Moon and Mercury. But we will need to retrain models because it doesn't like we need to learn the specific morphological specificity of craters on Moon and Mars, especially because of the space weathering, which erodate the craters a little bit differently. And also maybe incorporate different classes, other classes. Here I didn't talk about that, but we did not classify with central peak, double central peak, or the presence of central peak or not. Because our classes are like trans classes. You can have a central peak in a layered crater or in regular craters. So yeah, we choose other geomorphological categories. And yeah, then it was published in two scientific papers. So we are pretty happy about this. Thank you very much. So if you want more information about the paper, you can scan this QR code, or about me. I have a personal page you can visit, or just send me an email if you have questions. Thank you.
Thank you for that talk. We have one question online from Jamie, but I'm going to ask first, is there anyone in the room with questions, comments? All right, so Jamie's question is, have you considered Cohen's kappa to measure how much the agreements are due to chance?
No, I don't. To be honest, I don't know what is the name. I will just.
Yeah, I would say
open it.
grab it from the chat and do
Yeah.
an internet search for yourself
Yeah.
and see if that will help.
Yeah. I'm sorry, I need to learn myself about the Cohen's kappa test. Yeah, I will, but we did not have to do that.
Okay. In that case,
I have a question.
sorry,
I might have missed this, but what did you guys do differently from like previous similar work, like previous groups trying to do this? Because it seems like you had a better outcome in terms of recalling, from the hand mapped database.
Yeah, one of our major things remain in the pre-processing. The first thing we did is to reproject the images in order to have only circular shapes. And also, so this was a problem in studies I shown. And another thing we did is what we call in artificial intelligence stuff, data augmentations. So we basically, a crater is a crater, and if you turn it, it's also a crater. So with a single image of a crater, you can generate 100 situation of craters just by turning it from different angle or making translation or you see. And so this enables our model to learn all the specificities of the crater, even the one we didn't put in our databases. I don't know if it's answered.
It does make sense. Thanks.
Yeah.
Curious about the compute intensity. Is this require a supercomputer or process this? I mean, maybe I missed that.
No, I didn't say it. We used a non-made cluster that we have in our lab. It has 10 GPU. If you want, it's NVIDIA RTX Titan 10 or something, Titan X. I don't know yeah. And we computed for the detection. It was computed on one GPU. On each learning was on a single GPU, but we did several tests in parallel in order to converge to the good parameter composition. And for the classification, we use 8 in parallel for one training. It was during like 1 hour per training on 8 GPU. Yeah.
So it's obviously a huge amount of work to train this on a test data set and then compare it to the test data set. Where could you use this model now that isn't already counted, right? Like that always seems like part of the problem with this for me is you need to use so much of the work of the areas that have already been counted. It's a question of you couldn't just take it to the moon, right? You couldn't, so like, is there a good set of craters you feel confident you could use this on that hasn't already been counted or classified?
There's two things. So we applied it to the moon and to Mercury actually. I didn't show those results because they are not as good as expected, but actually it worked in a like satisfying way. So as I said, in perspectives, we wanted to do that properly by do vertical transfer learning, retrain the model to be able to have perfect scores on the moon. But now it works on the moon from now. It just still a little bit to improve. And then first, where to apply this, I show, oh, sorry, you can see, no, you can't see. Ah, I lost. When I presented my data sets, just this slide, I will try to share it. Share.
I think we've started moving towards the next talk to start staying on time, and I have the honor of my disembodied voice introducing Stuart. So I was hoping, can you move on to this question offline? Is that okay?
Yeah,
Yes.
sure.
We can come back to
Yeah.
And Clark had a question too. Can you ask it during the discussion? in an hour?
Yes.
Okay.
Okay, thank you very much.